Okay, welcome back. Last class we went through mathematical properties of fundamental equations, particularly the Euler equation and Gibbs Duhem expressions or equations. So today we are going to talk about generalized thermodynamic potential. Okay, start with this. So we essentially are going to focus on generalized thermodynamic potential. So why do we interested in this generalized thermodynamic potential? One of the reason is that so till date we have just discussed in the class only U and S. So U is a function of S, V, N1 till Nr, and S is a function of U, V. So these are natural variables corresponding to U and S. Okay, this essentially can yield all the thermodynamic properties of a system, whether it is a mechanical or thermal equation of state. So, so this can yield all the thermo info about a system. Okay. So one can do this exercise for a given system. One can use this expression of U and this variety of different constraints which we have looked into to come up with some equation of state, thermal or mechanical. But the problem is that most of the experiments which we conduct are not under constant entropy or volume or constant internal energy or volume in the moles. We mostly conduct those experiments at a constant temperature and pressure. Okay. So that brings a question that what would be the appropriate thermodynamic function when we have only temperature and pressure and moles, for example, constant. Okay, so usually experiments are usually conducted by controlling T and P. Okay, so thus the question is that it will be convenient if we can find appropriate thermodynamic function where the natural variable is T and P. Okay. Convenient to use natural variable T and P instead of, let us say, instead of S and V. Okay. So this is something which we would like to find a thermodynamic function where the natural variable is a Tp. So thus the question is there is a function of Tp, N1 and Nr that contains the same complete thermodynamic function as in U and S. Contains the complete thermodynamic information. Okay. Okay. So that is a very simple question which we are trying to raise, that okay, we would like to find the appropriate thermodynamic function where the natural variables are T, P, N, which contains the same complete information as in U and S. So the question is, how do we obtain a function with different variable from the original fundamental relation okay. So that is the question. So let us consider a very naive approach. Okay, so let us say if you start with function u, so you may have this u as a function of s, and you have this function u of s. Okay. So, what we can consider very naively that we can have this s u as a function of s. I am ignoring the other terms, and you take the derivative of s, okay, which is nothing but basically t of s, and then you invert t1 some function t1 such that t, which essentially is going to be s. So, for example, t, if you consider t1 as, so corresponding to this would be your del u1 by del s, and if you invert, which you can consider, let us say somehow if you can invert, then s is going to t1 inversion some function t1 of t, okay, and if you plug in the original, plug in to the original function, okay, then you may obtain something like u1 tilde of t. This is nothing but u1 of t1 by t. Okay. Now, with this kind of very simple derivative based inversion, the problem is that let us say if you have two function u1 which you have considered this, and u2 let us say is also a function of s, which is nothing but a simple shift here. In that case, if you take this derivative inversion process, which is a naive approach, you are going to get same as u1. So, if you try to take the derivative, obtain an inversion, and then you invert it back somehow, plug in the original, you are going to lose the information. That is what it says. If it is a simple approach like this, where if you consider two function which is just separated by a constant, then this would be the case where we are considering u1 t as well as u2 t. Okay. So, a simple approach like this is not going to work. Okay. So, we need to think in little more clever approach. So, this kind of approach which we have used here what is happening is information is getting lost in transformation. Okay. So, in order to obtain a suitable function, we will be making use of some mathematical approach, and that is called Legendre transformation. So, I am going to now describe that. Okay. So, the idea behind is that let us consider this is a function which is y as a function of x, and you have this this is let us say the curve, and what we are trying to do is now we are trying to define the slope at different points. Okay. So, this okay. So, okay. So, we have now let us say P1, P2, P3, this is a kind of slope, and the corresponding intercept would be phi . Okay. So, this is a kind of a slope. So, if you consider a generic definition of slope here, P would be something like this, y at that point minus the corresponding slope divided by x corresponding x minus 0. So, this would be the definition of slope. Okay. In other words, I can define phi as y minus p of x, all right. So, now what we are defining this particular function phi is basically we are saying this phi as a Legendre transformation or transform of y. Okay. Now, the question is how do you recover y? So, to recover y is equal to y of x given if phi is a function of phi p is given. So, at the end of the day, the problem with the naive approach was that if we want to invert it and want to return back to the original function, we will lose the information in this and that kind of transformation. So, we will be looking at how Legendre transformation works, where we would like to get back or recover the original function without losing it, and this is something we can see how it works here. So, if you want to recover this, let us look at it. So, recall that the definition of slope, so is also that P is also d of y by d of x. Okay, that is also the definition of the slope. So, this is also there, and as well as we can consider the y at that given point minus this intersect divided by the total x. So, this is also the definition. So, with this I can say d of y is nothing but p dx. Now, you can differentiate this expression. So, this will become d of y minus p dx minus x dp. Okay, this essentially is going to be 0. So, this is going to be minus x dp. Okay. So, this is going to be 0. So, you can recover this by a simple definition that minus x is nothing but d phi by dp. Okay. So, let us try to summarize here these two approaches or this particular approach, that in the case of y given as y of x, the definition we have to make use of is the definition of the slope. This is a Legendre transformation minus px plus y, and now here we were going to eliminate x and y to yield phi is equal to phi of p. Okay. Now, in the case of inverse, to recover the function, we are going to use phi is equal to phi of p. The definition is minus of x is d of phi by dp, and y now can be written as xp plus phi. Okay. So, here we are going to eliminate p and phi to recover or to yield y is equal to y of x. Okay. So, this is the Legendre transformation which we are interested in. Okay. So, let us now try to extend this for multiple variables. So, it is not just dependent only on x, but many other variables. So, that is what we can now generalize this. So, generalization okay. So, what we can consider now is y as a function of x0, x1, x3, and the derivative here can be written as p of k is equal to del y by del x of k. Now, this essentially means that there is a slope corresponding to one of the variable. Now, if you consider the Legendre transformation of the function phi, now here the phi would be p1 till p of t, and this is nothing but this is a family of tangent hyperplane. Okay. And the definition of phi would be y minus summation of all the slope multiplied by x of k. Okay. So, this is by definition here. So, if you take the derivative here d of phi, then you can show that this is nothing but minus summation x k dp k. Okay. So, this is something which is there. So, if you look at the definition of d phi, okay. So, this is your d phi is nothing but minus x multiplied by dp, right, where x is nothing but the partial nothing but the derivative. In this case, when you are considering many variables, the x of k would be nothing but del phi by del pk. Okay. So, again you have to pay attention to the details. What we have done is that we would like to generalize this expression. So, where the derivatives of this function is at a given with respect to a specific x k, where the rest of the variables are constant, is pk, and now we are defining this Legendre transformation function phi, which is a function of all these slopes, and that is why we are calling this as a family of tangent hyperplane. The definition of phi would be y minus summation p k x k. Now we are extending it for the one just variable, it was simply y minus p x, but now we are having many independent variables. So we are just saying summation p k x k, where x k is nothing but the partial derivatives of phi with respect to p k. Okay. So this is basically the Legendre transformation. So that means what we have done is y is equal to x1 xt. Now this we are getting a Legendre transform function phi p1 pt. So we have to eliminate phi and pk's. Okay. So that is something which we have to, if you want to do here, we have to eliminate y and x case. Okay. And whereas in the case of inverse is going to be phi and pk's. Now you may have situation where only not all the variables you would like to change, only let us say m plus 2 are independent variable, and in that case your function let us say is y as x0, x1, xm plus 1, xm plus 2 and so forth till xn minus 1. So if you are interested, let us say in some situation you might like to just take a Legendre transformation, which I am saying as LT, of only m plus 2 independent variable. So that means you would like to only change this, okay, or m plus 2 would be, okay, m plus 2 would be only this. Okay. So if you are interested in only this aspect, or to take the Legendre transformation, then your pk is going to be del y x k, where x of course j is not equal to k. That is what all the definition should be, because others are constant. So essentially when you are doing this, you are saying that x j is constant, but this is not equal to k, and similarly here as well. Okay. So this is by definition, but then k varies from 0 to m plus 1 for this specific case, where because we are only interested to take the Legendre transformation of only m plus 2 independent variable. Okay. So this is plus 2. So in that case what would be the Legendre transformation function? So this can be written as phi is equal to y minus summation k is equal to 0 m plus 1 p k x k. Okay. And therefore your phi is going to be phi p 0 p 1 till p m plus 1. This is a Legendre transformation of only m plus 1 variable, and then you have this x m plus 2 till x n plus 1. Okay. So we have been using a generic symbol such as y, but we can now interpret this y as some kind of a energy function such as u or s. So let us now try to use this Legendre transformation concept for transforming the variables from our basic fundamental relation expressions of u to something which we desire as far as the independent variables are concerned. So let us look at it. So if we interpret this function, now let us say we consider the case of energy. Okay, consider energy expression, or okay, or the expression of fundamental equation. Okay. So u is u as S1, and v or n1 till n some r. Okay. So this is nothing but, if you look at it, y is equal to function of y, x1 and so forth, right. So here basically x is this, v is this, these are the natural variables for basically the u. So what we want is to derive a corresponding to intensive variable. So, what we want is to derive an expression or function, derive a function corresponding to intensive variable t or p or mu. Okay, so this is what we want to do that. So let us look at it, and essentially what you're going to see that all the derivation has simply this particular kind of transformation where we are using Legendre function or transformation, okay, in energy or entropy, and essentially we are going to get the thermodynamic function. Okay. So, we are going to apply this thing, and we are going to get thermodynamic function which we call potential functions for different kind of independent variables, and that is something which you would like to see that. So, let us take a case and let us say okay. So, let us take a case first where we are going to look at U S V N N1 till N some, let us say T, and then we would like to get a function such as it is T V and T. Okay. So, essentially what we are trying to do is we are trying to change one of the variable this to T. Okay. Now, if you look at it the way we have done it in the expression here, that if you are interested in let us say m plus 1 variable to be Legendre transformed, then essentially we multiply the slope corresponding to the kth variable multiplied by the variable x. So, this is what we are going to do that, because here it is only one variable s to be converted to t. So, essentially our function should be something like this, the variable s. So, we do not know what is s at this point. So, let us first come up with the slope s or slope p. So, the p here is nothing but the derivative of del u by del s at a function of v, and all ni's are constant. Okay. So, this is the slope, right, by definition, and this value if you look at the basic thermodynamic function in differential form is du is T ds minus P dV plus summation mu I d n I. So, for the case of v n I is constant, du by ds is nothing but t. Okay. So, what we have is now a thermodynamic Legendre transformation function which is nothing but u minus Ts, and this is what we define. So, this is phi now, this is what we are defining is in order to differentiate this with different Legendre function which we are going to get. So, this function is now we call it A. Okay. So, this is nothing but is Helmholtz potential. Sometimes this is also called Helmholtz free energy. So, this free energy concept will come little later, but I am going to just write it down. Okay. So, now you have a function A which is nothing but u minus Ts, and remember now is A is a function with T v n1 c n t, right. So, if you take a differentiation of this A in our differential form, this is going to be d A is equal to du minus T ds minus s dt, right. Now, you can use here the basic definition of du, that will be T ds minus P dv minus s dt plus summation mu I d n I. So, there is another term here minus T ds. Okay. So, this get cancelled, this and this. So, what you have is minus P dv minus s dt plus summation mu I d n I. So, this is the differential expression of Helmholtz free energy or potential. Okay. That is something which came. So, now we have a function which basically has a natural variable T v n, and that is what A is, okay, the Helmholtz free energy. Now, this is one thermodynamic function Okay. Now, what about others? So, let us consider another function. We are saying that, well, in this case we wanted to have Legendre transformation from for the variable s to something we call it t, because we want to change the s to the derivative of du by ds, and that is nothing but t. But what about this where let us consider u as a function of sv, okay, and we want this to change only. The volume has to be changed in a way which is nothing but the derivative of u with respect to v, but which is nothing but, if you look at here, the derivative of u with respect to v and other variables are constant is nothing but minus p. So, we want to change this to p here. Okay. So, if you want to change this, what is the natural variable? So, let us look at it. So, p is the slope, is the pressure here. So, what we want to do is we want to consider the function u minus the slope multiplied by this variable v. The slope is nothing but del u by del v, and the rest s and ni's are constant, okay, and this is nothing but minus of p. Okay. So, you have a function u minus of minus p v, which is nothing but u plus p v. Okay. So, this is your Legendre function in order to change the variable sv, n1 and so forth to sp, and this we call it enthalpy. Okay. So, this is your enthalpy. Okay. So, enthalpy has a natural variable sp, n1 and nt. Okay. Now, if you want to show that this one of the important thing with the Legendre transformation is to obtain the original information using the inverse approach. So, that means the transformation back to the original does not lose any information. So, we should try and check whether we are getting the same if you redo this thing here, and here if I try this thing to get s and v back, okay, using the same approach here. Okay. So, do we get this u? Okay. So, we can try that. Now, dh here is going to be du plus p dv plus v dp, okay, and du we know this is nothing but tds minus p dv plus summation mu I d n I plus this here p dv plus v dp. Now, this gets cancelled. So, you have an expression T ds plus V dp plus summation mu I dni. So, if you look at the derivative of this function, so because we want to change p to its derivative, so that means we are talking about del h by del p, and s and rest are constant, then this is nothing but, if you look at this expression, okay, then this is nothing but u v. Okay. Right. So, we have to have a function now h minus v times p, and this is nothing but, if you look at the original expression here by definition, h minus p v is nothing but u. So, essentially you are getting back the original expression. Okay. So, that means we are not losing any information, this is the transformation. So, it makes perfect value to our mathematical means to convert from one variables to another variables. Okay. So, same thing we could have done that for a also. So, you can get back a minus del a by del t at constant v and n multiplied by t, and this is going to be a minus del a by del t is nothing but minus of s and t, and this is by definition is a plus T s, and this is nothing but, if you look at the definition of a, here a plus T s is nothing but u. So, you could do the same exercise for the Helmholtz free energy as well. Okay. Now, I can take it further for the case where we would like to change not just one variable, but then another variable. So, I will, but that can be done in the next class. I will take a break here, and then we will continue this exercise for obtaining the thermodynamic function appropriate of where its natural variables are T p, okay, and then we will try to summarize this exercise. Okay. So, I will see you in the next class.